Imagine drinking a glass of crystal clear water, breathing clean air inside a hospital, or trusting a gas mask to protect your life. Now imagine that all of those things depend on a black material that looks almost worthless. Think about this. Just 1 gram of activated carbon can have a surface area of more than 3,000 square meters. That's larger than many homes. But here's what nobody tells you. Creating that incredible material requires heat, chemistry, precision, and a journey that begins thousands of miles away from the factory. Most people never think about activated carbon. It hides inside water filters, gold mines, pharmaceutical plants, food factories, and emergency respirators. Every day, billions of liters of water pass through it. Every second, invisible pollutants become trapped inside its maze-like structure. And this is where it gets truly extraordinary. The material starts as ordinary wood, coconut shells, coal, or agricultural waste. Today, we're following activated carbon from farms, forests, and mines all the way to high-tech factories where fire transforms raw material into one of the most powerful purification tools humanity has ever created. You'll see temperatures hot enough to soften steel. You'll enter facilities where precision sensors measure particles smaller than grains of dust. And what happens inside the activation furnace may completely change the way you see this black powder forever. The journey often begins in Southeast Asia. Indonesia, the Philippines, India, Sri Lanka, and Thailand supply enormous quantities of coconut shells, one of the world's most valuable activated carbon feedstocks. Farmers harvest coconuts for food and oil, but the hard shells remain behind. For decades, many shells became waste. Today, they have become a global industrial resource worth millions of dollars every year. A typical coconut shell contains dense carbon-rich material with very low ash content. That makes it ideal for producing premium activated carbon used in drinking water purification. Trucks load several tons at a time and carry them to regional processing centers. Some shipments travel more than 5,000 kilometers before reaching their final manufacturing destination. Not all activated carbon comes from coconuts. In North America, Europe, China, India, and Australia, manufacturers often use bituminous coal, lignite coal, or anthracite. Deep inside open pit mines, gigantic excavators remove thousands of tons of rock every hour. The sound of steel buckets crashing into earth echoes across landscapes large enough to be seen from space. Some factories choose sustainably sourced hardwood. Others use bamboo or agricultural waste, such as nut shells and fruit pits. Imagine turning discarded biological material into a product that removes toxic chemicals from drinking water. What many people see as waste becomes a valuable industrial asset. That's a transformation few industries can match. Before manufacturing begins, laboratories inspect every incoming shipment. Technicians measure moisture content, ash levels, density, particle size, and carbon concentration. A batch with excessive contamination can reduce performance dramatically. In some facilities, even a few percentage points of impurity trigger rejection. But here's a supply chain secret most people never hear about. Transportation often contributes a surprisingly large share of the final environmental footprint. Raw materials move by truck, rail, ship, and conveyor systems before a single activation furnace ever switches on. Every kilometer adds cost, energy consumption, and emissions. Manufacturers now search for cleaner alternatives. Some facilities recover energy from production gases. Others use renewable electricity or source agricultural byproducts that would otherwise be burned or discarded. The industry continues balancing performance, cost, and environmental responsibility. And that balance becomes even more difficult once the raw material enters the hottest stage of the process. Because the moment these ordinary shells, woods, or coal particles enter a furnace, they begin a violent transformation. Temperatures soar, gases escape. Internal structures collapse and rebuild themselves. What happens next surprised even experienced engineers when they first witnessed it. And in the next stage, you'll see exactly how fire creates billions of microscopic pores that give activated carbon its astonishing power. The transformation begins with carbonization. Raw coconut shells, coal, wood, or other feedstocks enter large rotary kilns or vertical furnaces. Inside, temperatures climb to roughly 500 to 700 degrees Celsius, or 932 to 1,292 degrees Fahrenheit, while oxygen levels remain extremely low. You hear the deep rumble of rotating steel drums and the crackling sound of trapped gases escaping. The air smells smoky, earthy, and intensely hot as the material slowly turns into char. During carbonization, water vapor, tar compounds, methane, hydrogen, and other volatile materials leave the feedstock. What remains is mostly carbon. Imagine a structure losing everything unnecessary and keeping only its backbone. The material shrinks, darkens, and becomes fragile. Yet this is only the beginning, because the char still lacks a microscopic pore network that makes activated carbon extraordinary. Next comes activation, the step that gives activated carbon its name. Massive furnaces heat the char to between 800 and 1,100 degrees Celsius, or 1,472 to 2,012 degrees Fahrenheit. At these temperatures, operators inject steam or carbon dioxide under carefully controlled conditions. Think about this. Engineers intentionally burn away part of the carbon structure. They destroy material to make the final product more powerful. Inside the furnace, carbon reacts with steam through a simplified reaction. Carbon plus water vapor produces carbon monoxide and hydrogen. The reaction slowly eats away sections of the carbon matrix. Tiny pores open, then smaller pores connect to larger ones. What began as a solid structure becomes a labyrinth so complex that a single gram can contain billions of microscopic adsorption sites. What happens next surprised even experienced engineers when activation technology first matured. Manufacturers intentionally sacrifice up to half of the original material mass. A shipment of several tons may lose thousands of kilograms during processing. Yet the material becomes far more valuable because every lost particle helps create new internal surface area. It's one of the rare industries where less becomes more. Depending on the product specification, activation can last anywhere from 30 minutes to several hours. Rotary kilns may turn at 1 to 3 revolutions per minute, while carefully moving material through temperature zones. Sensors constantly monitor heat, gas flow, oxygen concentration, and residence time. A small mistake can reduce adsorption performance dramatically. After activation, the carbon exits the furnace at temperatures that can exceed 800 degrees Celsius. Cooling systems immediately take over. Water-cooled conveyors, inert gas chambers, or specialized cooling vessels reduce temperatures before the material encounters normal air. Without careful control, hot activated carbon can ignite unexpectedly. Now, the factory enters a phase that looks more like mineral processing than chemistry. Crushers reduce oversized pieces into manageable fragments. Industrial grinders spin hundreds or even thousands of RPM, depending on design. The sound becomes deafening. Vibrations travel through the floor as black carbon moves through steel machinery. Screens and classifiers separate particles by size. Some customers need powdered activated carbon finer than flour. Others require granular products with carefully controlled dimensions. High-speed vibrating screens sort thousands of kilograms every hour. Under bright factory lights, streams of black particles move with almost liquid-like precision. For specialized applications, manufacturers add another step. Activated carbon enters pelletizing systems, where binders help form uniform cylindrical pellets. Powerful presses shape thousands of pellets every minute. These products often serve air purification systems because they allow gases to flow efficiently while maintaining high adsorption capacity. Before packaging, dust collection systems capture fine particles from the air. Giant filtration units continuously remove airborne carbon dust. You hear powerful extraction fans roaring overhead. Most people never think about this hidden infrastructure, yet it protects workers, improves product quality, and reduces waste. Finally, automated filling systems load the finished product into bags, drums, super sacks, or bulk transport containers. Robotic arms stack pallets with astonishing speed and precision. A product that started as a discarded coconut shell or a piece of coal now stands ready to purify water, recover gold, remove industrial chemicals, or protect human lives. But here's the question that keeps factory managers awake at night. How do you know every single batch performs exactly as promised? How do you measure billions of invisible pores and guarantee reliability for drinking water systems, hospitals, and critical industries? The answer lies inside laboratories packed with technology that can see what the human eye never will. The moment activated carbon leaves production, A different kind of factory takes over. This one doesn't rely on fire. It relies on data. Most people never think about this, but some facilities test dozens of quality parameters before a single shipment leaves the warehouse. Every batch must prove it can perform exactly as promised. Inside the laboratory, technicians measure iodine number, molasses number, moisture content, ash content, hardness, particle distribution, and adsorption capacity. Automated analyzers process samples with extraordinary precision. Tiny variations can affect performance in water treatment systems, handling millions of liters every day. In some applications, even small deviations matter. Automation plays a massive role throughout the process. Conveyor sensors track product movement in real time. Laser scanners monitor particle flow. AI-powered vision systems inspect packaging lines and detect labeling errors instantly. Thousands of data points stream into control systems every minute. Some facilities reject between 1% and 3% of production before shipment. Defects can include excessive moisture, improper particle size, contamination, or reduced adsorption performance. Automated systems catch most problems. Yet there are moments when technology reaches its limits. And this is where human skill still beats machines. Experienced technicians can sometimes recognize subtle changes in texture, flow behavior, or appearance before instruments trigger alarms. Years of observation create instincts that software cannot fully replicate. Even in highly automated factories, human judgment remains essential. International customers often require strict compliance with standards and certifications. Production systems may follow ISO quality frameworks, environmental management systems, and industry-specific requirements for drinking water or food applications. Every document, test result, and production record becomes part of a traceable history. Before approval, some batches undergo durability and hardness testing. Machines repeatedly stress particles to determine whether they can survive transportation and industrial use. The carbon may travel thousands of kilometers, pass through large treatment systems, and operate for extended periods. Reliability isn't optional. It's the entire business. Yet even after passing every inspection, another mystery remains. How much activated carbon does the world actually need? The answer reveals an industry far larger than most people imagine. Activated carbon has grown into a massive global industry. Annual production exceeds several million metric tons, supporting water treatment, food processing, pharmaceuticals, mining, chemical manufacturing, and environmental cleanup. The global market generates billions of dollars in value every year. What started as a niche filtration material now supports critical infrastructure across the planet. China remains one of the largest producers, followed by major manufacturing activity in India, the United States, Indonesia, and several European nations. Together, these regions account for a substantial share of global supply. Massive export networks move activated carbon across oceans and continents every day. Few consumers ever realize how international this industry truly is. Think about this. If global annual production were loaded into freight trains, the line could stretch for hundreds of kilometers. If packaged into small household water filter cartridges, the number would reach into the billions. The scale becomes difficult to imagine because activated carbon often remains hidden inside products people use. The industry's growth accelerated dramatically over the last 50 years. Rising environmental standards increased demand for cleaner water and cleaner air. Governments introduced stricter regulations. Industries adopted more advanced filtration systems. As pollution concerns grew, activated carbon became one of the world's most trusted purification technologies. Did you know that activated carbon helps recover gold from mining operations? In some processing plants, dissolved gold attaches to activated carbon surfaces before engineers extract and refine it. A material that cleans drinking water can also help produce precious metals. Most people never hear that story. Did you know that activated carbon supports emergency response equipment used around the world? Specialized grades remove dangerous gases and airborne contaminants from respirators and protective systems. In critical situations, microscopic pores can become life-saving technology. That's a remarkable responsibility for material that looks like black dust. And here's perhaps the most surprising fact of all. Scientists continue developing new forms of activated carbon for emerging challenges, including advanced water purification, energy storage, and environmental remediation. What began as a simple carbon material continues evolving through modern research. The next decade may transform the industry once again. From tropical coconut farms and vast mining operations to furnaces hotter than molten lava and laboratories measuring invisible pore structures, you follow one of manufacturing's most fascinating journeys. What looks like an ordinary black material carries an extraordinary story of chemistry, engineering, logistics, and human ingenuity. Every particle represents energy, precision, and decades of technological refinement. The next time you pour a glass of clean water, walk through a filtered building, or see advanced industrial purification systems at work, remember the hidden material making it possible. Most people never notice it. Most people never think about it. Yet activated carbon quietly improves daily life for billions of people around the world. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.